Hello everyone, welcome to Civil Galaxy. I am Dr. Pruthviraj B S. Today we shall see how to analyze a propped cantilever overhanging beam with the help of consistent deformation method. So in order to analyze this structure, my first step will be to find out the degree of static indeterminacy. So to find out the degree of static indeterminacy, first I should know the number of reactions. So if I consider this particular propped cantilever overhanging beam, at support A, I will be having one vertical reaction at point A. Similarly, I will be having a moment about point A. Also, I will be having one horizontal reaction about point A. Similarly, at point B, I will be having one vertical reaction about point B. So, here I am having the total number of reactions I am having is 4 and the number of available equilibrium equations are 3. So, now if I want to find out my degree of static indeterminacy, which will be equal to 1. So, I am having one extra force, so that force needs to be treated as my redundant force. So out of these four forces, if I consider reaction about point B in the vertical direction as my redundant force, in my step 2, I will treat reaction about point B in the vertical direction as the redundant force, So now the same propped cantilever overhanging beam can be treated as a cantilever beam. This is point A. So from point A to point D, where I am having a point load of 60 kilonewton at a distance of 2 meters. This is point D. So from D to B, it is 2 meters. Again from B to C, where there is a point load of 30 kilonewton, this point C, distance is 2 meters. So now I need to find out the downward deflection for this external loading. So for that I will use, so for further analysis to find out the deflection, that is the downward deflection, I will use a unit load method. I will use unit load method for downward deflection. As we know from unit load method, if I want to find out the deflection, we are going to consider a unit load. Similarly, if we want to find out the rotation, we will consider a unit moment. So now, applying a unit load about point B where I have considered the redundant force, I will apply a unit load about point B. That means I will remove all the external loads and I will apply only one unit load about point B. This is point A, this is point D, 2 meters from point A. Similarly, this is point B, 2 meters from point D. Here I am going to apply a unit load. From B to C again it is 2 meters. So now again I have to find out the downward deflection of this particular beam by using the unit load method, applying a unit load about point B. If I closely observe here, I am having 3 portions, that is B to C, B to D and D to A. So now if I just write the deflection here for this particular beam due to external loading, I am going to get a deflection here about this point. I can call it as deflection from, for this portion particularly, delta C to B. Similarly, I am going to get a deflection about this point where I am going to call deflection for this portion B to D. Similarly, I am having a deflection about this point. I will call it as deflection from B to D. And at the support, my deflection will be equal to 0. That is delta A is equal to 0. Similarly, if we observe, if I want to find out the deflection here due to the unit load, the deflection will be in this fashion. So now I want to find out the deflection only about the point where I am applying the unit load. Similarly, here also there will be a deflection. That means I have to find out the deflection for each portion due to the external loading, and also the deflection due to the downward deflection due to the applied unit load. So for that I will consider a table. So for that, for my convenience, I will consider a table to further analyze the structure, where I will take it as, first one is called as portion. So for that particular portion, as I told, I am having three portion here, that is C to B, first portion. Similarly, I am having second portion here, B to D. Similarly, I am having one more portion here, that is from D to A. So now for this particular portion, I have to find out the origin. So if I consider from C to B, the origin, the first point here is C. So I will consider the origin as my point C. So from B to D, my origin will be B. Similarly, from D to A, my origin will be D. So for that particular origin, I need to apply the limits. So if I consider the portion C to B, I am having a distance of 2 meters. So the limit will be here from 0 to 2. Similarly, for portion B to D, the limit here will be 0 to 2, as it is 2 meters here. So from D to A, it is having a 2 meters. So the limit here will be also 0 to 2. So now for this particular beam, I have to find out the moment due to external loading, where I will call it as capital M. This is called as moment due to external loading. Similarly, I will find out small m, that is moment due to the point load or unit load. Next, I have to find out the flexural rigidity EI. Here in this beam, EI is constant, so I can say for all the portion my EI is constant. So now if I want to find out the moment about this point, for this three portions here, I have to consider sections as per the unit load method. So if I consider about point or portion BC, I have to consider only this portion. So first capital moment, that is moment due to external loading, I have to take one section. Here. I will take a section XX at a distance of X from the origin. So now if I want to find out moment for this particular portion, moment about this point, force multiplied by perpendicular distance, since it is an cantilever beam, it is subjected to a hogging bending moment, it will be negative. So the distance, the loading here is 30 kilonewton and the distance here is X. Be force multiplied by perpendicular distance rotating clockwise, creating a hogging moment, it will be negative. Similarly, if I come for portion B to D, that is moment due to external loading, I have to consider a section about this portion from B to D here. So now this distance from here to here will be equal to X. So now if I want to consider moment for this portion BD about this point here, force multiplied by perpendicular distance. I know force is 30 and the distance from this point C up to here is, from C to B it is 2 meters, and from B to D it is x, so it will be 2 plus x. Rotating in the clockwise direction, creating hogging moment, it is considered as negative. Next, if I want to take the moment due to external loading for portion dA, I will consider a section in the portion D to A from here. So now I am having, that is force about this point, force multiplied by perpendicular distance. So from here to here, if I consider, I am having a distance of 4 meters. I am having a distance of 4 meters. So I want to consider moment about this point. Force multiplied by perpendicular distance will be 30 into 4 plus x, which is negative. Similarly, I am having one more force here. That is force multiplied by perpendicular distance. Here the distance will be x. So minus 60 into x. So now similarly, if I want to find out moment due to the applied unit load for portion CB, since the unit load is applied at point B, the portion about point, the moment about the portion CB will be equal to 0. So now similarly for portion B to D, if I want to consider moment due to unit load, I will take a section here x at a distance of x. Similarly, force multiplied by perpendicular distance will be equal to 1 and the distance is x. It is negative since it creates a hogging moment. Similarly, for portion D to A, if I want to take the moment due to unit load, I will consider one section here, a distance of x. So force multiplied by perpendicular distance, here it will be minus 1 into 2 plus x. So now further analyzing this structure, I know from Castigliano's second theorem, I can consider, if I want to find out a deflection, which will be equal to integration of the limit 0 to L, that is moment due to external loading into moment due to unit loading divided by EI into dx. So now my objective here is to find out the deflection about point B. I want to find out the deflection about point B, which will be equal to my deflection of all these three portions, that is deflection about point C to B plus deflection about point B to D and the deflection in the portion D to A. So now I have to calculate each of this deflection, so I am able to achieve my object to find out the deflection about point B. So for that I have to take deflection about the portion CB first, which will be 0 to L, integration from 0 to L, m multiplied by small m divided by EI into dx, which can be represented as moment due to external loading, moment due to unit load. So I will write here for your better understanding, where capital M will be moment due to external load and small m is nothing but moment due to unit load. So So now if I observe the portion CB here for the deflection, a CB, M I am having, that is, I am having a limit from 0 to 2, already I have mentioned the limit here, and the capital M is minus 30 into x. Similarly, I am having the moment due to unit load is nothing but 0 divided by EI into dx. So this comes to 0. So hence my deflection about point CB will be equal to 0. So similarly, I need to find out the deflection about the portion BD, that is deflection about point BD. So similarly, if I just apply the same formula here, my limit will be from 0 to 2, and my capital M for the portion BD is nothing but minus 30 into 2 plus x, and here the moment due to unit load is minus x divided by EI into dx. So now further simplifying this, I will be having 0 to 2, that is 60x plus 30x square divided by EI into dx. So now further simplifying this equation. So if I further simplify the equation, I will be having, if I take out 1 by EI outside, I will be remaining with, so 60x plus 30x square into dx. So now if I integrate it, there is limit from 0 to 2. So now if I integrate it, I am going to get 1 by EI multiplied by 60x square plus 30x cube by 3. The limit will be from 0 to 2. So now if I further simplify this for the deflection about the portion B to D, my value comes out to be 200 by EI. This is my deflection in the portion B to D. Similarly, I need to find out the deflection in the portion D to A. Similarly, I need to find out my deflection in the portion D to A. So for that, I'll just consider the values of the moment due to external loading and unit load which I have got here from this table. Which will be that is minus 30 into 4 plus x minus 60x, that is capital M, into minus 1 into 2 plus x. So now if I further simplify this, I can rewrite it as, the limit will be from 0 to 2, that is 240 plus 60x plus 120x plus 30x square plus 60x square divided by EI into dx. So here also divided by EI into dx. So now if I further simplify this equation, So now if I further simplify this particular equation, so now simplifying this equation further, I am having this 0 to 2, which will be, or which comes out to be 240 plus 300x, 240 plus 300x plus 90x square divided by EI into dx. So now if I take out 1 by EI outside, I will be remaining with if I integrate 240x plus 300x square by 2 plus 90x cube by 3. The limit is from 0 to 2. So if I further simplify this, the deflection in the portion D to A comes out to be, 1320 by EA. Comes out to be 1320 by EI. So now I have got all the 3 deflections for each portions. So putting the values for all the deflection in each portion, where my delta B will be equal to, so this I know it was 0, deflection about point or portion CB was 0. Similarly, the deflection in the point or in the portion BD was 200. It's 200 by EI. Similarly, the deflection about the portion D to A is 1320 by EI. So now the deflection about point B comes out to be 1520 by EI. So now to further analyze this structure, I have to, in the third step, so in step 3, so if I consider step 3, I have to find out the upward deflection due to the redundant reaction alone. That means I will consider the beam, this is A, similarly this is point D, and I have considered the reaction, vertical reaction about B as the redundant force. So I have to apply the redundant reaction here, that is vertical reaction about point B. This is point C having a distance of 2 meter. This is B, this is 2 meter, and this is also 2 meter. So due to this upward deflection or the applied due to this applied redundant reaction, my deflection will be in this way. So now this deflection here, I will consider it as Y. So now from the previous class we know the standard deflection equation. If I want to find out the standard deflection equation, which comes out to be, whenever a cantilever beam is subjected to a point load in the midspan, I am having W A cube by 3 EI. So here W can be considered as reaction at point B in the vertical direction. I am going to get reaction about point B in the vertical direction. A is nothing but the total distance from point A up to the redundant reaction here, which comes out to be 4 meters. So here it will be 4 cube divided by 3 EI. So now if I want to find out the deflection here, which will be reaction about point B into 64 multiplied by 3 EI. So this I will call it as my equation number 2. Similarly, I will call this as my equation number 1. So now my step 4 is the final step. In the final step, I have to compare these two equations, that is applying the compatibility equations, that is equation 1 will be equal to equation 2. So equation 1 I am having, that is delta B should be equal to my Y. That is the value here comes out to be of delta B 1520 by EI, which will be equal to 64 reaction about point B in the vertical direction divided by 3 EI. So EI gets cancelled here. My reaction about point B in the vertical direction comes out to be, if I simplify, comes out to be 71.25 kilonewton. 71.25 kilonewton. So now, if I just come for the beginning here, out of 4 forces, I have got one force, that is reaction about point B in the vertical direction. I am remaining with another 3 unknown reactions. So to further find out the unknown parameters, I will take summation of all the vertical forces to be equal to 0. That is nothing but here reaction about point A in the vertical direction plus reaction about point B in the vertical direction. That is, and summation of all the vertical forces. Here I am having a vertical download force, that is minus 60 minus another load which is coming downwards, that is 60, to be equal to 0. So now further simplifying this one, reaction about point A in the vertical direction plus 71.25 is the value of RBV here, reaction about point B in the vertical direction, minus 60 and minus 30 will be equal to 0. So if I further simplify this, my reaction about point A in the vertical direction comes out to be 18.75 kilonewton. So I have got the second parameter. So now the remaining parameter is a reaction about point A in the horizontal direction. Since there is no horizontal force, my reaction about point A in the horizontal direction will be equal to 0. Next, I want to find out moment about point A. So finding out moment about point A will be for this particular point here. I know moment is nothing but force multiplied by perpendicular distance. That is, the force here is 30 and the total distance here is 6. So it will be 30 into 6, rotating in the clockwise direction, creating a hogging moment, will be negative. So here reaction about point B in the vertical direction, force multiplied by perpendicular distance, rotates anti-clockwise, creating a sagging moment which is positive. That is 71.25 into 4 minus force multiplied by perpendicular distance, that is minus 60 into 2. So if I further simplify, my moment about A will be equal to minus 15 kilonewton meter. So if I want to summarize, There were 4 reactions. We have got 4 reactions initially. That is reaction about point A in the vertical direction. Similarly, reaction about point B in the vertical direction, reaction about point A in the horizontal direction, and moment about point A. So, I wanted to find out all these unknown parameters. So, RAV I have got, that is 18.75 kilonewton in the upward direction. Similarly, reaction about point B I have got, that is 71.25 kilonewton, that is 71.25 kilonewton in the upward direction. Similarly, reaction about point A in the horizontal direction is 0 since there is no horizontal force. Similarly, moment about point A is minus 15 kilonewton meter rotating in the anti-clockwise direction. So we shall see further problems in the next coming classes. Thank you.